Hello and welcome to our course on machine learning with Python. In this course, we'll be studying the theory of machine learning and how to use popular Python libraries to implement machine learning models using the Python language. So, let's begin. This course is divided into 10 sections. We'll be going through these sections one by one. The first is an introduction to machine learning. In this section, we will learn about the fascinating world of machine learning. After that, we will study 4 practical machine learning algorithms, which are regression, classification, clustering, and recommender system. Alright, let's now begin with our first section, which is an introduction to machine learning. So, what is machine learning? Machine learning is a form of artificial intelligence where the machine are taught to do tasks without being explicitly programmed. The goal of machine learning is to understand the structure of data and then fit that data into models that can be understood and utilized by people. Machine learning has the following characteristics. First, we feed machines with some data, and the machine learns the relationship amongst those data. Second, based on that relationship, it can predict events for other data. And third, its performance improves with time, which means it has some intelligence like humans. I believe I won't be wrong to say that the machine learning is almost everywhere. It has so many applications. For instance, it is used for medical diagnosis, self-driving cars, spam email filtering, stock market trading, automatic language translation, product recommendations, traffic predictions, image recognition, speech recognition, and in many more applications. Here are some specific examples of the application of machine learning. Number 1. It is used to detect cancer and brain tumors. Number 2. Tesla, the car manufacturing company, is working on self-driving cars using machine learning. Number 3. Our Gmail separates spam emails into a different folder from the important emails, and it uses machine learning algorithms to do that. Number 4. Google Translator uses machine learning algorithms to translate text from one language to another. Number 5. Netflix, YouTube, Amazon, and other such companies recommend products to users, products which the user might be interested in. Again, this is only possible because of machine learning. Moreover, Google Maps, face detection to unlock a device, Siri, Cortana, Alexa, all these technologies are used machine learning in the background. In machine learning, tasks are generally classified into broad categories. These categories are based on how learning is received. 2 of the most widely adopted machine learning methods are supervised learning and unsupervised learning. In the coming lectures, we will study them in detail. In supervised learning, the computer is provided with example inputs that are labeled with their desired outputs. The purpose of this method is for the algorithm to be able to learn by comparing its actual output with the taught outputs to find errors, and modify the model accordingly. Supervised learning therefore uses patterns to predict and put label values on the unlabeled data. As we can see in the figure, we have provided the data set with the labels. So on the basis of the input labeled dataset, the model will predict the class of the test data set as square and triangle. A common use case of supervised learning is to use historical data to predict statistically likely future events. It may use historical stock market information to anticipate upcoming fluctuations. Or tagged photos of dogs can be used as input data to classify untagged photos of dogs. Next is unsupervised learning. As the name suggests, in unsupervised learning, the data is unlabeled. So the learning algorithm is left to find commonalities amongst its input data. As we can see in the figure that we have provided, we have given raw data without labels as input. And then the algorithm divides data into different groups based on their similarities. So it groups dogs and cats separately. The unsupervised learning approach can discover hidden patterns within a data set that are needed to classify raw data. As unlabeled data are more abundant than labeled data, machine learning methods that facilitate unsupervised learning are particularly valuable. In this lecture, we'll discuss the two concepts, supervised and unsupervised learning, and how to frame them mathematically. I'm going to explain the idea of how we might mathematically describe what supervised and unsupervised learning really implies in terms of meaning. The two key ideas here are supervised and unsupervised, which are the two most prevalent paradigms in data science. There is also reinforcement learning, which has a different structure, but we'll not discuss it here. In this lecture, we'll focus on the difference between two concepts, supervised learning and unsupervised learning. Supervised learning is when you provide the data with labels, which is what the supervision means. Unsupervised learning is when you give it no information about the data, and it must discover patterns in the data in order to exploit and represent them back to you. I'll show you an example to demonstrate this. While supervised learning involves placing labels on your training dataset to give the algorithm a heads up on what you want it to do, unsupervised learning involves just tossing data into the pot and asking it to detect patterns. Here you see a bunch of grey dots, and your job is to write an unsupervised learning algorithm that can tell you how to cluster and classify this data. Here it's a pretty easy to see that there's one cluster here and one cluster over there. So what we'd like to do is create an algorithm that, just like our naked eye, can tell us that these two clusters are distinct. One thing to note here, when these clusters get closer together, it's a lot more difficult to tell where are the clusters, and even if there is any clusters at all. Because I don't tell you anything other than the position of each dataset in some state space, your task is to tell me whether or not there is one cluster, two clusters, three clusters, four clusters, or even more clusters of the same kind of data. To put it another way, your performance metrics will always be better in a supervised context. Here is how it works in a supervised setting. I'll give you some data, and you'll have to decide whether the remaining grey balls belong to one of the two classes, either blue or red. Your job is to decide which class the remaining grey balls belong to. As many of you have noticed, this really helps because you'd say, anything in this cluster here is going to be blue, and over there, anything in this cluster is going to be red. When I mix them, you can see that I've created a much tougher classification work, but you can see mainly that the blue balls are here and the red balls are there. So this is the beginning of the structure of what we need to understand about supervised and unsupervised learning. It all comes down to the training labels. Later in this course, we'll go through some of the most popular leading methods for both supervised and unsupervised learning, so that you'll have a better understanding of the principles involved. By now we have a proper idea of what machine learning is in general. Soon we will be diving deeper into it along with its programming implementations. But before doing that, we need to set up our environment in order to be able to do that. The programming language that we are going to use is the Python language. Python is a programming language which is very much used in data science. One of the reasons behind the popularity of this language is that it's well established and has robustly defined libraries. Such libraries are NumPy, SciPy, Matplotlib, Pandas, and scikit-learn. Let's go ahead and see what kind of libraries we have. First, we have the NumPy library, which helps to deal with large multi-dimensional arrays and matrices along with a large collection of high-level mathematical functions that can be performed on these arrays. Second, we have SciPy, which is used for scientific computing and technical computing. SciPy contains modules for optimization, linear algebra, integration, special functions, signal and image processing, and other tasks common in science and engineering. The third is Matplotlib. It is a plotting library and it is easy to use with NumPy because it's numeric and because it is integrated with NumPy. Next is Pandas library. It's designed for data manipulation and analysis. In particular, it offers data structures and operations for manipulating numerical tables and time series. Last is scikit-learn, also known as sklearn. It is a free machine learning library for the Python programming language. It features various classification regressions and clustering algorithms, and it is designed to incorporate with the Python numerical and scientific libraries NumPy and SciPy. In this course, we'll be working with Python 3. Python 2 is an outdated version of Python and is no longer supported. The following graph shows the popularity of Python 3 versus Python 2 over the last 5 years. And as you can see, Python 2 is hardly in the competition. To install Python in Windows, go to python.org. Click Downloads. Download the latest version of Python 3. At the time of recording this video, the latest version is 3.9.7. Let's download it now. After the installation is finished, open the file. This will open the installation wizard. Make sure that Add Python 3.9 to Path is checked. Click Install now. Wait for the installation to finish. After the setup is finished, type Python in your search bar and click idle, open brackets, Python 3.9 64-bit, close brackets. Python idle will open up. Python idle is an integrated development environment for Python that allows you to create, modify, and execute Python scripts. It also provides features like syntax highlighting and auto-completion. Once Python idle opens up, type print brackets hello, close all brackets, and press enter to execute. You will see the output in the next line. To install Python in Mac, head towards python.org. Click Downloads. Download the latest version of Python 3. Once downloaded, open the file. An installation wizard will open up. Click Continue. Click Continue again and again. Read and accept the license agreement. Click Continue. Next, click Install. You may be required to enter your password. Wait for the installation to finish. If the installation was successful, Python was installed on your machine. To open Python idle, search for idle in your Spotlight and open it. Type print brackets hello world, close brackets, and hit enter to execute it. The integrated development environment I am going to use for coding is Jupyter Notebook. I recommend you to use Jupyter as well. The Jupyter Notebook is a web-based open source software that enables you to write and share live code, equations, visualization, and narrative writings. We have completed this section of the course. Here is a question for you to answer. Which of the following is true about unsupervised machine learning? Number 1. Unsupervised learning comprises algorithms with no pre-existing outcomes. Number 2. Learning algorithms with no control over quality of their predictions. Number 3. A semi-autonomous machine learning where researchers control some parts of the modeling process. Number 4. A fully autonomous machine learning with no human interference. The correct answer for this question is choice number 1. Unsupervised learning comprises algorithms with no pre-existing outcomes. Alright folks, the next section of this course is about regression. Let's move on. To download Anaconda, click on the link given in the slides. It will take you to Anaconda's website and will automatically detect operating systems. Click Download. After the download is finished, open the file. Click Next. Read the license agreement and click I agree. We recommend choosing Just Me and click Next. If you want to change destination directory, click Browse and select your destination folder. Then click Next. Click Install. It takes a while to install. Once it is installed, click Next. Click Finish. If the installation was successful, Anaconda will be installed on your machine. To launch Jupyter Notebook, search for Anaconda Navigator in your search bar and open it. Inside the Anaconda program or Anaconda Navigator, you will see a tab called Jupyter. Launch your Jupyter Notebook by clicking on Launch. It will launch Jupyter Notebook in your default web browser. By default, Anaconda runs in your home directory. We will look into navigating through different directories in a while. For the time being, click New and then Python 3 to create a new notebook. The following interface will open up. We will talk more about the interface soon. To set up Anaconda on Mac, click on the given link. Next, click on Started. Click Download Anaconda Installers. We recommend installing the graphical installer unless you are comfortable with command line. In this tutorial, we will be downloading the graphical installer. Let's click on it. After the download is complete, double click on the file to start the installation wizard. Click Continue. Read the README file and click Continue. Read the license agreement and click Continue. Select Destination folder and click Continue. Next, click Install. If you would like to install PyCharm on your Mac, you can visit the given link. However, it's not required. Let's click Continue. Once the installation finishes, click Close. If the installation was successful, Anaconda will install on your machine. Search for Anaconda Navigator in your Spotlight and open it. Launch Jupyter Notebook. This will launch Jupyter Notebook in your browser. Create a new notebook by clicking on New and then Python 3. An empty Jupyter Notebook will open in another tab. We will talk more about the interface at a later stage. To set up Anaconda on Ubuntu, open your terminal by pressing Ctrl, Alt, and T. Copy-paste the following command and hit Enter. Next, copy-paste this command and hit Enter again. Next, we move to the Downloads directory by giving the following command. Once in the Downloads directory, copy-paste the following command in your terminal and hit Enter. Next, give the following command and hit Enter. When prompted, hit Enter again. License agreement will now be displayed on your screen. To scroll through license agreement, keep pressing the Enter key. Read the agreement and then type Yes and hit Enter. Press Enter to install Anaconda in the home directory. After a while, Anaconda will be installed on your machine. When asked, Do you wish the installer to initialize Anaconda 3 by running conda init? Type yes and hit enter. After the installation is successfully finished, restart your terminal. You will now see base written before your directory name. This is the command line interface for Anaconda, which runs on the Ubuntu terminal. To launch Jupyter Notebook, type Jupyter Notebook without the quotation marks and hit enter. This will launch Jupyter Notebook in your default browser. To create a new Jupyter Notebook, click on New and then Python 3. An empty Jupyter Notebook will open in another tab. We will talk more about the interface soon. And now on to the next lecture. This is Jupyter Notebook interface that we saw earlier. Jupyter Notebook has a cell-based structure which allows us to have code, visualization, mathematical equations, and narrative text all at one place. You can have as many cells as we want. For the time being, let's just stick to writing Python code in Jupyter Notebook. In the cell, type print brackets hello world close brackets and click on the run button. The output of a cell is produced right below it. Now on to the next lecture. Next, we will have a look at managing directories in Jupyter Notebook. To open Jupyter Notebook in a particular directory, copy the path of that directory. In your search bar, type Anaconda prompt and open it. Anaconda prompt is the command line interface for Anaconda. This will open Anaconda prompt in your Windows directory. If your desired directory is in a different drive, you need to first change the drive. In this case, we want to move to drive D. We type D and hit enter. Note that Anaconda prompt is not case sensitive. Next, to move to the desired directory inside the D drive, we give the command cd and then paste the path that we had copied earlier. Hit enter. Finally, to launch Jupyter Notebook, type Jupyter Notebook without quotation marks and hit enter. After a while, Jupyter Notebook will open up in your default browser. If you have an existing notebook in your directory, you can open it by clicking on it. Otherwise, you can create a new notebook. Let's click on this hello.ipynb to open it. Our hello.ipynb contains just one line of code, a print statement. To open Jupyter Notebook in a specific directory in Mac, open the directory in Terminal. Type Jupyter Notebook without the quotation marks and hit enter. After some time, Jupyter Notebook will launch in your browser. You will be able to see the files in the directory where Jupyter Notebook is running. In this case, we have one notebook called hello.ipynb. Let's open it by clicking on it. This is our hello.ipynb file with just one print function. Now onto the Ubuntu operating system. To open Jupyter Notebook in a particular directory, open that directory in the terminal by right-clicking and selecting Open in Terminal. Type Jupyter Notebook without quotation marks and hit enter. It takes a while to launch Jupyter Notebook. After some time, Jupyter Notebook will launch in your default browser. As you can see, we already have a notebook called hello.ipynb. Let's open it by clicking on it. And here you go. Hello.ipynb contains a single line of code, a simple print function. That was all for managing directories in Jupyter Notebook. And now on to the next lecture. Regression is a statistical method which predicts a relationship of a continuous outcome based on the value of one or more input variables. It is used in many disciplines such as statistics, economics, finance, investment industries, data science, and more. Some real world examples for regression analysis include predicting the price of a house given house features, forecasting sales based on input parameters, predicting the weather, and etc. Regression can be divided into two types. One is linear regression and the other is non-linear regression. In linear regression, the relationship between input variables and the output variable is linear. In other words, an equation of a line can define the relationship between input and output. Now, keep in mind that linear regression can be further divided into, number 1, simple linear regression, and number 2, and multiple linear regression. Simple linear regression involves only a single input variable, and that single input variable is used to predict an output. While in multiple linear regression, more than one input variable is involved. Now, when it comes to non-linear regression, the output can be represented as a function that is non-linear combination of the inputs. Let's have a look at how linear regression works. In the given table, I have the prices of each house depending upon the area of the house. Using this data, we will build a machine learning model that can predict the price of a 330 square feet apartment. You can plot available prices and areas in scatter plot. On the graph, it is done with red dots. Now we can draw different lines to try to fit these red points. We can draw many lines. They seem to fit to our model, but which line fits the best? To find out the best fitted line, what we do is the following. We calculate these delta values that you see here on the screen. Delta 1 and delta 2, these variables represent the error between the red dots and the line. Then we square individual errors and we sum them up. We follow this procedure for each line that could potentially be a good fit for our data points. After performing these computations, we come up with the following conclusion. The blue line that you see on screen is giving me the minimum error, so I choose this specific line for my model. The next step is to use this blue line in order to predict the price of any house we want. I assume you are already familiar with the line equation. Y is equal to m times x plus b, where y is the dependent variable of the independent variable x. M is the slope of the line and b is the y-intercept. Here is the representation of the equation of the line in terms of area and price. Where price is dependent variable and surface area is the independent variable, because we are calculating the price based on the surface area. We are going to find out the best fitted value for M and B. Then we predict the price of any house when the surface area is given as an input. Now we're going to write a simple Python code for doing home price predictions. Import Panda as PD. Import NumPy as NP. Import matplotlib.pyplot as PLT. From sklearn.linear _model, import linear regression. Here I have launched my Jupyter Notebook and I have imported some useful libraries. First, we need to bring the data to our system. We have a dataset named homeprices.csv, which consists of a table containing area and price data. So I'm going to load the data from our CSV file to a pandas data frame. So I'm going to type df equals pd dot read underscore csv brackets home prices dot csv close brackets df. Run this cell. So, to load the data from my CSV file, I used the pd.read underscore CSV function and passed the name of the files as an argument, as you can see on your screen. Now, the next thing that I'm going to do is to plot the scatter points of our data just to get an idea on how the points are distributed. I'm going to plot a graph of area versus price. So, I'm going to write plt.xlabel brackets area brackets again square foot close all brackets. plt.ylabel brackets price another bracket US dollars close all brackets. plt.scatter brackets df.area comma df.price comma color equals red comma marker equals plus close brackets. The first two lines of code set the X and Y labels of the graph. We named them X label and Y label as area square foot and prices in US dollars, respectively. In the third line, we have used the scatter method. This draws the X, Y coordinate points in the graph. In our case, the points are the area and price. Moreover, we have some optional arguments for the function, such as color and marker. The color tells which color we want our points to be printed, and markers tell us what the shape of those points should be. Next, we print the graph and see the distribution. From the plot, I get an idea that the distribution is suitable for a linear regression model. Points are not randomly distributed. Points are moving up and right. Now I'll go ahead and use the linear regression model. So, first you need to create a linear regression object. I will write reg equals linear regression brackets. From the sklearn library, we imported the linear model. I will create an object for linear regression and then I will fit my data. So now I write reg.fit brackets df square brackets area close square brackets df.price close all brackets. When I say that I will fit my data, I mean that I'm training the linear regression model using the available data points. In this first argument, I have supplied a data frame which only contains the area, and then in the second argument, we have the y-axis, which is our price. Once I run this code, our model is ready to predict the prices. So let's do a prediction. We want to predict the price of house whose surface area is 3,300 square feet. We write reg.predict brackets and square brackets 3,300 close all brackets. Run this cell. And here you go. We get an output. And we can see that it predicted the price, which is 628715.75342. So when I trained my model with the given data set, it calculated the coefficients and intercepts. So let's see what the values of these coefficients are. Reg.coef underscore will show the value of the m coefficient. And when we do reg.intercept underscore, this will show the value of the B coefficient. So, by using these values of coefficient and intercept, we can calculate the price of a house. So, I'm going to write 135.788 star 3300 plus 180616.438. Run the cell. And here you go. We get exactly the same result as before. So now you know how the simple linear regression works and how to implement it in Python. Next, we will be learning about the multiple linear regression. Let's go! You can see the graphical representation for simple linear regression on the left, and for multiple linear regression on the right side of your screen. The difference is only due to the fact that multiple linear regression has more than one input or independent variable, which means that the output depends on each input. Therefore, there will be a unique linear correlation between each input and the output. These correlations are shown by 4 different lines on the graph on the right side of the screen. The mathematical illustration of the multiple linear regression is y equals a plus b1 x1 plus b2 x2 plus b3 x3 plus b4 x4, where a is the y-intercept and b1 is the slope of the line that represents the relationship between the output and the first independent variable x1. b1 indicates that if we increase the value of x1 by 1 unit, then b1 tells us that how much the output value will be affected. Regarding b2, b3, and b4, they all work in a similar fashion. For the implementation of multiple linear regression, we are going to use a CSV file containing 5 columns and 50 rows. In this data, we have the 4 independent variables called R&D spend, administration, marketing spend, and state. And there is one dependent variable, profit. Our task here is to train a machine learning model with this data in order to understand the correlation between each of the 4 independent variables and predict a profit for another new company when all these 4 independent variables are provided. Okay, so here I am in Jupyter Notebook. First, as usual, we need to import the required libraries. Import the libraries. Import NumPy as NP. Import matplotlib.pylot as PLT. Import pandas as PD. Then we store the dataset 50_startups.csv as a pandas data frame in a variable called dataset, using the function pd.read_csv. So I'm going here, leave a note of what I'm doing. Reading the dataset, then we write the code. Dataset equals pd.read_csv brackets 50_startups.csv close brackets. Next, we use the .iloc function to slice the data frame in order to assign indices to x and y. I will write the following. x equals dataset.iloc square brackets colon comma colon -1 close square brackets dot values. Y equals dataset.iloc square brackets colon comma -1 close square brackets dot values. Here we have square brackets colon comma colon -1 close square brackets, which can be interpreted as include all rows, include all columns up to -1, excluding -1. In these lines of code, -1 refers to the first column from the last. Thus, we assign the 0th, first, second, and third column as x. We assign the last column -1 to dependent variable which is y. Then we print the data frame to see if we have got the correct columns for our training data. So I write dataset.head brackets 5. And here are the values we expected. If the values are numbers in the dataset, we can easily apply mathematical computations on the dataset and create prediction models. In this dataset, we come across a non-number variable like the variable state. Such data are called categorical data. We need to convert those categorical values to numerical values somehow. We encode this categorical data using another important library called sklearn from sklearn.compose import column transformer. From sklearn.preprocessing import one hot encoder. CT equals column transformer brackets transformers equals square brackets encoder comma one hot encoder brackets comma square brackets 3 close all brackets remainder equals pass through close brackets. X equals np.array brackets ct.fit underscore transform brackets x close brackets. In this piece of code, we imported the column transformer and one hot encoder. In our case, we need to use the one hot encoder to transform our state column index number 3 to numerical data. The column transformer constructor takes quite a few arguments, but we're only interested in 2. The first argument is an array called transformers, which is a list of tuples. The array has the following elements in the same order. Name, a name of the column transformer, which will make setting of parameters and searching of the transformers easy. Next is transformer. Here we're supposed to provide an estimator. We can also just pass through or drop it if we want. But since we're encoding the data in this example, we'll use the one hot encoder here. Remember that the estimator you use here needs to support fit and transform. Next is columns, the list of columns which you want to be transformed. In this case, we'll only transform the 4th column. The second parameter we're interested in is the remainder. This will tell the transformer what to do with the other columns in the dataset. By the default, only the columns which are transformed will be returned by the transformer. All other columns will be dropped, but we have the option to tell the transformer what to do with the other columns. We can either drop them, pass them through unchanged, or specify another estimator if we want to do some more processing. As you can see here, we named the transformer simply encoder. Next, we use the one hot encoder brackets constructor to provide a new instance as the estimator. And then we're specifying that only the fourth column has to be transformed. We're also making sure that the remainder columns are passed through without any changes. Once we have constructed this column transformer object, we have to fit and transform the dataset. To do so, we have the next line of code. It takes the dataset X and transforms the values of the attribute state to numeric using one-hot encoder. Moreover, this code takes all values from the transformed X dataset and converts it to an array. After encoding our dataset, you can see the fourth column has now been transformed and it has become the first three columns. The values 0, 0, 1 represents New York. The values 0, 1, 0 represent Florida, and 1, 0, 0 represents California. So now our whole dataset is numerical and ready to work with. Amazing! We're now well equipped to manipulate our data set. Let's move on. The next important task is to split our dataset into training set and test set. We do this in order to train our model with one portion of the data called the training set, and then we test the prediction results on the other set of data called the test set. Alright, let's do this. We write from sklearn.model underscore selection import train underscore test underscore split x underscore train comma x underscore test comma y underscore train comma y underscore test equals train underscore test underscore split brackets x comma y comma test underscore size equals 0.2 close brackets. What did we do here? We used the train underscore test underscore split function to split our data. Here, we give the test underscore size a value of 0.2, which indicates that 20% of the data is the test set. In our case, 10 random startup data will be chosen as the test set, and 40 remaining startup data will be chosen for the training set. In the next step, we need to write the following. From sklearn.linear underscore model, import linear regression. Regressor equals linear regression brackets. Regressor dot fit brackets x underscore train comma y underscore train close brackets. So what did we do here? We imported the linear regression class which we are going to apply to our training set. We assigned a variable called regressor to the linear regression class. We then used the regressor.fit to fit the training dataset, x underscore train and y underscore train, to this linear regression class for the training process to occur. Now we are going to predict the profit values of the test set using the trained model, regressor. So let me first write the code and then explain it. We create a y underscore pred variable. Y underscore pred equals regressor dot predict brackets x underscore test close brackets. Then another variable called df. df equals pd dot dataframe brackets real values colon y underscore test comma predicted values colon y underscore pred close brackets. Then we print df. So what did I do here? I used the regressor.predict function to predict the values of our test data, x underscore test. We assign the label predicted values to y underscore pred. We now have two data sets, y underscore test, which are the real values, and y underscore pred, which are the values that we predicted. Next, we compare both values to see how our model has performed. We printed both the values of y underscore test as real values and y underscore pred values as predicted values of each x underscore test in a pandas data frame. In this way, we obtain the values for all of the 10 x underscore test data points. We can see our predicted values are pretty close to real values overall. For first value, the real values is 65200.33 and the predicted values is 69622.870630. We see that the model has closely predicted this value and hence we can say that our model has a good accuracy. But the question before us is, how good? Like, how good is this accuracy? Do we have a method to measure it? Fortunately, we do. Let's now move on to the next lecture and see how we can measure this accuracy. On the screen, you can see three scales to measure the performance of a model. The first one is mean absolute error, MAE. It is the mean of the absolute value of the errors. N is the number of values. Yi is an actual value. And yi hat is a predicted value. So we subtract a predictive value from the corresponding actual value and then we take its absolute value and add them all together. Then we divide everything by n. This value gives us a proper sense of how much error there is, or in other words, how accurate our model is. Similarly, we have the mean squared error, MSE, which is the mean of the squared errors. And then we have the root mean squared error, RMSE. This is the square root of the mean of the squared errors. Now we will see how to implement one of these model evaluation scales in Python. We'll be working using root mean squared error. It is already defined in the sklearn.metrics module. So let's write the following. RMSE from sklearn import metrics print np dot sqrt brackets metrics dot mean underscore squared underscore error brackets y underscore test comma y underscore pred close all brackets. So what did I just do? I imported the module evaluation scale from the sklearn library, root mean squared error in our case. We imported and input our actual and predicted values as argument to it. So that's how we can measure the error of a model. Congratulations, we have completed the regression part. Before moving on to next session, let me ask you a question. Which of the following evaluation metrics can be used to evaluate a model? Why modeling a continuous output variable? A. AUC-ROC. B. Accuracy. C. Log loss. D. Mean squared error. The solution is D. Mean squared error. Since the linear regression gives the output as a continuous values, so in such case we use mean squared error metric to evaluate the model performance. The remaining options are used when dealing with classification problems. We will discuss classifications in the coming section. So, what is classification? Classification in machine learning and statistics is a supervised learning approach in which the computer program learns from the data given to it and makes new predictions or classifications. Here are some applications like filtering emails, speech and handwriting recognition, biometric, fingerprint recognition, and etc. For example, in the fingerprint recognition system, the system will recognize the fingerprint of the specific person as it is trained by different fingerprints of different persons. So, with the help of classification, the system will identify the class of fingerprint that a specific person belongs to. The algorithms for classification are neural network, regression, and k-nearest neighbor. K-nearest neighbor is a supervised learning technique which measures the similarity between two classes. As we can see in the figure, we have two categories A and B and a new data point which is the blue color. The KNN classifier will assign to it a category on the basis of similarity. It will assign the new data point to the category for which the number of neighbors is the highest. So, it is assigned to category A in this case. Here is a formula to calculate the Euclidean distance. The Euclidean distance is the distance between 2 points. By calculating the Euclidean distance, we get the nearest neighbor. Let me now explain to you what k-nearest neighbors are with a simple example. Suppose we have an input image that could be either a dog or a cat. We don't really know. In this example, the input image is more like a cat than a dog. To perform KNN in Python, we will use the dataset called userdata.csv. It is attached with the materials of this course. Let's see what information this dataset contains. Dataset equals pd.read_csv brackets userdata.csv close brackets. Dataset. Let's run the cell. The dataset contains lots of information. The estimated salary and age are the variables that we will consider for the independent variables, and the purchased variable is for the dependent variable. The steps we are going to perform while coding are the following. Pre-processing, fitting KNN to the training set, predicting the test result, and then testing the accuracy of the results. In the next lectures, we'll perform these steps one by one in Python. First of all, we will import the required libraries by writing the following. Importing the libraries import numpy as np. Import matplotlib.pyplot as plt. Import pandas as pd. From sklearn.metrics import confusion_matrix. Then we will import the dataset to our system and put independent variables into x and dependent to y. So we write the following. Importing the dataset. Dataset equals pd.read_csv brackets userdata.csv close brackets x equals dataset.iloc square brackets colon comma 2 colon 4 close square brackets dot values. Y equals dataset.iloc square brackets colon comma 4 close square brackets dot values. Print brackets x print brackets y. Let's run this cell. And here you go. You can see that using the iloc function, the values of column index 2 to 3 are put in the variable x, and similarly column index 4 of dataset is put to variable y. In this next step, we will split our dataset into testing and training and define the percentage of how much of our data we want to use as training or testing data. So I will write training and testing data. Here I will divide the data into two parts. From sklearn.model_selection, import train_test_split x_train, x_test, y_train, y_test equals train_test_split brackets x, y, test size equals 0.25, random state equals 0 close brackets. In this code we have used 0.25 or 25% of the data as a testing data and the remaining for the training dataset. Then we will import a scaling method called standard scaling. So I write from sklearn.preprocessing import standard scaler. sc_x equals standard scaler brackets x_train equals sc_x dot fit underscore transform brackets x underscore train close brackets x underscore test equals sc underscore x dot fit underscore transform brackets x underscore test. We scale our data in Python to normalize the data into a specific range. It is useful to scale the input attributes for a model that relies on the magnitude of values. We have used the fit method here to scale our data. What it does is that it takes a dataset to scale as input and it returns the scaled data, which is again saved to the same variables x underscore train, x underscore test in our case. By executing the above code, our dataset is imported to our program and well pre-processed. After feature scaling, our test dataset will look like this. Now our dataset is scaled and now we fit the KNN classifier to the training set. Here we need to fit the KNN classifier to the training data. So we write from sklearn.neighbors import kneighbors classifier. Classifier equals kneighbors classifier brackets n underscore neighbors equals 5, comma metric equals Minkowski, comma p equals 2 close brackets classifier dot fit brackets x underscore train, comma y underscore train close brackets. So what did I just do here? First, I have imported the define kneighbors classifier class from the sklearn neighbors library. After importing the class, we created the classifier object of the class. The parameter of this class will be n underscore neighbors. It will define the required neighbors of the algorithm. Usually, it takes 5. Metric equals Minkowski. This is the default parameter and it establishes the distance between the points. P equals 2. It is equivalent to the standard Euclidean metric. And then we will fit the classifier to our training dataset. Fitting a classifier to a dataset means that the classifier trains and predicts output based on the training data. Here we are first predicting the results for x underscore test data. We assign the values to y underscore pred. Now we have predicted values of the classifier and the actual values as well. If we want to compare both values and measure the accuracy of our model, we need some method. One of the matrices used for comparison is confusion matrix. A confusion matrix is also known as an error matrix. It is a summary of prediction results on a classification problem. The matrix you see on your screen is confusion matrix. Which tells us that 64 trues values are correctly predicted true. 3 false values are incorrectly predicted true. 4 true values are incorrectly predicted false. 29 false values correctly predicted false. The result shows that there are 64 plus 29 equals 93 correct predictions and 3 plus 4 equals 7 incorrect predictions. Our next topic is decision tree. So what is the decision tree technique? It's a kind of supervised machine learning technique in which the data is being split continuously based on parameters. It breaks down a dataset into smaller and smaller subsets. The final result is a tree with decision nodes and leaf nodes. A decision node, example age, cholesterol, has two or more branches. The leaf node, example middle age, represents a classification or decision. The learning algorithm of decision tree is as follows. First, it chooses a feature from the given data set. Then it determines the importance of the feature in the segmentation of data, and the data segmentation will depend upon the best feature. After that, we repeat the above steps. All those processes use some kind of criteria and measurements in order to make decisions. One of the such criteria is entropy. Let's see what entropy means in the next lecture. So what is entropy? Entropy is the measure of the amount of uncertainty or randomness in the data. Intuitively, it tells us about the predictability of a certain event. For example, consider a coin toss that has a probability of heads of 0.5 and a probability of tails of 0.5. Here the entropy is the highest possible since there's no way of determining what the outcome might be. Alternatively, consider a coin that has heads on both sides of the coin. The entropy of such an event can be predicted perfectly since we know beforehand that it'll always be heads. In other words, this event has no randomness, hence its entropy is zero. In particular, lower values imply less uncertainty, while higher values imply high uncertainty. So while choosing parameter for each node in a tree, the decision tree measures this value and choose the one with high certainty. The dataset we are going to use for implementation in Python is the following. Here, we want to predict if a person's salary is more than $100,000 based on the company, his job title, and the degree that he has. Now, when you look at the dataset and when you give it any human being to solve this problem, that human being naturally try to build a decision tree in their brain. Now we're going to build a decision tree algorithm in Python for the given dataset. Our tree would have the following structure. Nodes, which represent the parameters. They will be connected to each other for every combination. We should have a final yes or no answer. This is how our decision tree would look like till the second depth. By second depth, I mean there are two layers of nodes. The first layer has only a single node, and this node represents company, which means our tree is branched according to the companies. So, the next layer of nodes represent different companies, such as Google, Facebook, ABC, Pharma. And we do not have further nodes. So, this tree has two depths. According to our dataset, our decision tree tells us that if a person works at Facebook, then yes, he or she would have a salary higher than $100,000, regardless of the degree and position. To implement in Python, as usual, first we will import the required libraries and classes. The classes which is new here compared to the previous example is the decision tree classifier, class of the sklearn tree library. We will see how to use it in order to implement our decision tree in Python. Again, like previously, we need to bring the dataset to our system first. In the first line, we created a list of names of columns from our data. Next, we are reading the data set with column names corresponding to the above list. So, at this point, we all know that machine learning algorithms work on numbers and not on the labels. So, we will convert our columns which have labels into numbers. For this, we will use the label encoder. So, from sklearn, I have imported pre-processing. Next, I have created an object of label encoder class from pre-processing. Next, I have called the fit_transform function of the label encoder class on the company column. This line of code takes label inputs from the company column and encode those values to numbers, then assign it back to the same column. In this way, all the label values of the column company from our data are converted to numeric. Similarly, you can do the same for the job and degree columns in the data. Next, to see how our data looks like, we print a few rows of our data using the head function. By default, the head brackets function is used to get the first 5 rows. You will do the same for the salary more than 100k column. So, I'll need to write number sign split the dataset in features and target variable. Feature underscore cols equals square brackets company, comma, job, comma, degree, close square brackets. X equals data, square brackets, feature underscore cols, close square brackets. Y equals data, open square brackets, salary, underscore, more, underscore, then, underscore, 100k, close square brackets. X equals data dot values, square brackets, 1, comma, 3, close square brackets. Y equals data dot values, square brackets, 1, comma, 3, close square brackets, 1, comma, 3. 1 means we are not using the header. Print brackets X, print brackets quotation marks, print brackets Y. We run this cell, and here you go. This is how our variables X and Y look like. Now, similarly to train and test our model, we need to split data into x underscore train, comma, x underscore test, comma, y underscore train, comma, and y underscore test. This is what we need to do here. So, I'll write x underscore train, comma, x underscore test, comma, y underscore train, comma, y underscore test equals train underscore test underscore split brackets x, comma, y, comma, test underscore size equals 0.2, comma, random underscore state equals 100, close brackets. And we run this cell. Now we are ready to train our classifier. We use a decision tree classifier class to create a decision tree. Let's go and see how we can do this in Python. So, first we create decision tree classifier object using entropy. So I write create decision tree classifier object using entropy clf underscore entropy equals decision tree classifier brackets criterion equals entropy, comma, max underscore depth equals 3, close brackets. Next, we train the decision tree classifier. So I write train decision tree classifier CLF underscore entropy equals CLF underscore entropy dot fit brackets x underscore train comma y underscore train close brackets. Next we need to predict the response for the test dataset. But before that, let me explain what I just did. The decision tree classifier class takes two arguments. The first argument is the criteria that is going to use to create a decision tree, and that criterion is, in our case, entropy. The second argument is the number of maximum depth that our tree will have. In our case, we have specified it as 3. Okay, so now that the blueprint model of our decision tree is built, we need to fit it to our data. We do it with the fit function, similar to our previous models. After doing so, the model is ready to predict and evaluate. So, I write, predict the response for test data set. Y underscore pred equals CLF underscore entropy dot predict brackets x underscore test close brackets. Then print brackets accuracy comma metrics dot accuracy underscore score brackets y underscore test comma y underscore pred close brackets close all brackets. And as you can see, the accuracy of our model is just 75%. Great! In this section, we will discuss another classification algorithm, that is logistic regression. We will see, number 1, what is logistic regression, and number 2, its implementations in Python. In this lecture, we will discuss what is logistic regression. Logistic regression is used to predict the likelihood of a specific class or occurrence. Here are some conditions to make use of logistic regression. If the information is binary, if you require probabilistic outcomes, when a linear decision boundary is required. So, these are the conditions. So, there are many applications of logistic regression as well. For example, it is used to forecast survival in wounded patients in the medical profession, to estimate the likelihood of a person suffering a heart attack, to predict the likelihood of a procedure or product failing, and to predict a homeowner's possibility of defaulting on a lender. In the next lecture, we will see how logistic regression works by implementing the algorithm on a dataset. There is a dataset given in the attached documents which contains the information of various users obtained from social networking sites. The dataset is shown in the following image. In this problem, we will predict the purchased variable, dependent variable, by using age and salary, independent variables. We are going to follow the same steps that we have performed in KNN, and they are pre-processing, fitting logistic regression to the training set, predicting the test result, testing the accuracy of the result. In the next slides, we will perform these steps one by one in Python. So, we will import the libraries. I'll write importing the libraries, import numpy as MP. Import matplotlib.pyplot as PLT. Import pandas as PD. From sklearn.metrics, import confusion_matrix, and we run this cell. We then import the given data set by writing the following. I first keep a small note of what I'm doing. Importing the data set. Dataset equals pd.read_csv brackets user data.csv close brackets. Then we will extract independent and dependent variables. So I write x equals dataset.iloc square brackets colon comma square brackets 2 comma 4 close square brackets close all square brackets dot values. Y equals dataset.iloc square brackets colon comma 4 close square brackets dot values. In the next step, we will split our dataset into testing data and training data. We'll also specify the percentage of how much of our data we want to use as a training or testing data. So, to split my data, I'll need to write the following. Training and testing data, brackets, divide the data into two parts, close brackets. From sklearn.model_selection, import train_test_split. x_train, x_test, y_train, y_test equals train_test_split. Brackets x, y, test_size equals 0.25, random_state equals 0, close all brackets. And we run this cell. So what did I just do? I first imported the training and test split method from sklearn.model_selection, and then I divided my data into training and testing sets. In this code, we have used 0.25 or 25% of the data as a testing data, and the remaining for the training data set. Now, we will perform pre-processing on our dataset. We will pre-process the data so that we can use it in our code efficiently. So, to do that, I will write from sklearn.preprocessing import standard scalar sc_x equals standard scalar brackets x_train equals sc_x dot fit_transform brackets x_train close brackets x_test equals sc_x dot fit_transform brackets x_test close brackets, and we run this cell. So, what did we just do? We imported the sklearn library for our algorithm, and we scaled the data features to a specific range. By scaling, we tried to bring all the variety of ranges of the features, values to a specific range so that our algorithm will understand better how much an attribute affects the model and performs better. By executing the above code, our dataset is ready to be fed to the classifier. After feature scaling, our test dataset will look like this. Now our data is scaled and next we are ready to go. We can see the data being scaled to the range of -2 to 2. By scaling it, it has meant that we bring our data values in a specific range. In our case, we scaled our data values to the -2 to 2 range. We have well prepared our dataset, and now we will train the dataset using the training set. To provide training or to fit the model to the training set, We will import the logistic regression class of the sklearn library. So I write from sklearn.linear_model import logistic regression. After importing the class, we will create a classifier object and use it to fit the model to the logistic regression. So I'll write classifier equals logistic regression brackets random underscore state equals 0 close brackets. Here our classifier is learning the parameters to fix the data and find a pattern. After training the classifier on our training data, in the next lectures we will see how we will use the classifier to predict the outcome of our test data. To predict the results, we'll create a y_pred vector and then create a confusion matrix from the sklearn library. So I write y_pred equals classify.predict brackets x_test close brackets. Then I say here what I'm doing, making the confusion matrix. Then I continue with the code. cm equals confusion_matrix brackets y_pred comma y_test close brackets print brackets cm. We run this cell. And here you go. You can see the confusion matrix. The confusion matrix is a matrix used to show the number of predicted values and number of actual values. We use it to show how accurate our model is by comparing the total number of predicted values to the corresponding actual values. The result shows that there are 68 plus 32 equals 100 correct predictions and 0 incorrect predictions. This is the accuracy of our classifier. Out of 100 predictions, 100 are correct predictions and 0 are wrong predictions. We can use the confusion matrix to see the correct and incorrect predictions. We can create a nice heat map of our confusion matrix using the Seaborn library. So to do that, I need to write the following: sns.heatmap brackets cm. We run this cell, and here you go. You can see the heat map. In the next lecture, we will compare logistic regression to the linear regression. Even though they sound similar, they are quite different. We'll see next what are the similarities and the differences while using these types of regressions. So, when we're dealing with logistic regression, we estimate the values of categorical variables. However, when dealing with linear regression, our goal is to estimate the outcome of continuous variables. So, to sum it up, categorical variable estimation is done through logistic regression, while continuous variable estimation is done through linear regression. Next, in logistic regression, we discover the S-curve, which gives the boundary of the categorization. For example, if our predicted value is above the S-curve, then we put it in one category, and if it is below, then we put the data point in the other category. Alright, so we discover the S-curve in logistic regression and use it to categorize the samples. We use sigmoid function to find the S-curve. However, in linear regression, we look for the best fit line, which allows us to predict the outcome with ease. In logistic regression, it is not necessary to have a linear connection between the dependent and independent variables. But in a linear regression, it is necessary that the connection between the dependent and independent variables is linear. Lastly, for logistic regression, there should be no collinearity between the independent variables. While for linear regression, there is a possibility of collinearity between the independent factors. One similarity in both of them is that they both can be used for regression, while logistic regression can also be used for classification, as we saw in this section. That's it for this section. I hope you liked it and learned about the key differences between logistic and linear regression. And now on to the next lecture. Here is a quick question before we move on to next section. Is logistic regression mainly used for regression? A. True, or B. False? The answer is false, because logistic regression is a classification algorithm. Don't get confused just because there is the word regression in it. Our next topic is clustering. So what is clustering? Clustering is the task of grouping a set of objects in such a way that objects in the same group form a cluster. It is an unsupervised learning technique. As we can see in the diagram, arbitrary colored points are being separated into classes by clustering. Here are some applications of clustering. They include pattern recognition, spatial data analysis, image processing, document classification, finding pattern of weather behavior, and so on. In this lecture, we are going to discuss why we need clustering. And we're going to see the tasks for which we can use clustering. As we already know, clustering is used to separate the randomly available data into similar groups of data. We can use clustering for the following techniques, like analyzing data from research, creating a summary, detecting noise, duplicate detection, and so on. All these tasks can efficiently be performed using clustering. In the next lectures, we are going to discuss the algorithms of clustering, which are k-means clustering, hierarchical clustering, density-based clustering. K-means clustering is an unsupervised learning algorithm, which groups the unlabeled dataset into different clusters. It's an iterative algorithm that divides the unlabeled dataset into k different clusters in such a way that each dataset belongs to only one group that has similar properties. The letter k defines the number of predefined clusters that need to be created in the process. It allows us to cluster the data into different groups and in a convenient way. This will allow it to have the category of groups in the unlabeled dataset by itself and without the need for any training. As we can see in the picture, the data is being categorized into similar groups. The steps of k clustering are the following. First, partition clustering. Second, without any cluster internal structure. K-means divides the data into non-overlapping regions or groups. And third, within a cluster, the examples are very similar. Now, finally, we note that various clusters have quite different examples. So, how do we determine the optimal value for k? First, we need to keep in mind that the performance of the k-means clustering algorithm depends on the highly efficient clusters that it forms. Hence, choosing the optimal number of clusters is a big critical task. There are some different ways to find the optimal number of clusters, but here we are discussing the most appropriate method to find the number of clusters or value of k. The method given below is the elbow method. The elbow method is one of the most popular ways to find the optimal number of clusters. As you can see in the formula below, we have the sum of the distances between each data point and its centroid squared. And all of this is within cluster 1. Then we add to it the sum of the distances between each data point and its centroid squared. And it's all within cluster 2. And the same goes for the third term. It is the sum of the distance squared within cluster 3. Now, to measure the distance between the data points and the centroid, we can use any method such as the Euclidean distance or the Manhattan distance. To find the optimal number of clusters using the elbow method, we follow the steps mentioned on screen. Since the graph shows a sharp bend, which looks like an elbow, this method is known as the elbow method. The graph for the elbow method looks like the image below. The steps of the elbow method are the following. It executes the k-means clustering on a given dataset for different k values. They range from 1 to 10. For each value of k, it calculates the WCSS value. It plots a curve that shows us how the calculated WCSS values varies with the numbers of cluster k. The sharp point of bend looks like an elbow, and that point is considered as the best value of k. Next, we will see the code for the elbow plot and all the steps implemented. First, we'll get the k-means algorithm from the library of sklearn. So, I write, finding the optimal number of clusters using elbow method. From sklearn.cluster, import k-means. Then we'll initialize the list for the values of WCSS. So I'll need to write WCSS underscore list equals brackets, initializing the list for the values of WCSS. Using 10 iterations, we will create a k-mean cluster and fit it on our dataset, X in this case. So I write 10 iterations for I in range brackets 1, 11 close brackets colon k-means equals k-means brackets n underscore clusters equals I comma init equals k dash means plus plus comma random underscore state equals 42 close brackets. K-means dot fit brackets x. WCSS underscore list dot append brackets k-means dot inertia underscore close brackets. X is a sample dataset which we obtained from sklearn.datasets. Based on this dataset, we're going to implement k-means clustering in the upcoming slides. The code k-means equals k-means brackets n underscore clutters equals I close brackets will create I number of clusters 1 to 10. We will add the values inertia values into our WCSS list using WCSS underscore list dot append brackets k-mean dot inertia underscore close brackets. The inertia underscore method measures how well a data set was clustered by k-means. It is calculated by measuring the distance between each data point and its centroid, squaring this distance and summing these squares across each cluster. Then we plot the values of k, or clusters, on the x-axis and the values of the corresponding WCSS underscore list values on the y-axis. So to do that, I write plt.plot brackets range brackets 1, 11 close bracket, comma WCSS underscore list close all brackets, plt.title brackets the elbow method close brackets, plt.xlabel brackets number of cluster close brackets, plt.ylabel brackets WCSS underscore list close brackets, plt.show brackets. We used the dot plot method and gave our x values, our iterations 1 to 10, and y values the corresponding 10 inertia underscore values from WCSS underscore list. As you can see, we also give the title using the plt.title brackets method. We then named the x and y label as well. At the end, we used the show brackets method to plot our graph. In our next lectures, we will see other algorithms for clustering. In this lecture, we will discuss another type of clustering, which is hierarchical clustering. Hierarchical clustering involves creating clusters that have predetermined ordering from top to bottom. For example, all files and folders on the hard disk are organized by hierarchy. In this type of clustering, we can see how different subclusters relate to each other. There are two strategies of hierarchical clustering. One is divisive and the other is agglomerative. Divisive is top-down, so you start with all the observations in a large cluster and break it down into smaller pieces. Think about divisive as dividing the cluster. Agglomerative is the opposite of divisive, so it is bottom-up, where each observation starts in its own cluster and pairs of clusters are merged as they move up the hierarchy. Let's now talk about the density-based clustering. It depends on the density of the cluster. It locates the region of high density and separates the noises. The db-scan algorithm is a type of density-based clustering. It can find out any arbitrary shaped cluster without getting affected by noise. For instance, if a particular point belongs to a cluster, it should be next to many other points in that cluster. It works based on two parameters. One is radius and the other one is minimum points. Epsilon determines a specified radius. Now, if that radius includes enough points within it, we can call it a dense area. M determines the minimum number of data points we want in a neighborhood to define a cluster. The algorithm proceeds by arbitrarily picking up a point in the dataset. If there are at least m points within a radius of epsilon to the point, then we consider all these points to be part of the same cluster. Here are some advantages. It can discover arbitrarily shaped clusters. It can find clusters surrounded by a different cluster. And it is robust towards noise detection. Let's implement our k-means clustering in Python. So I'll need to write %matplotlib inline from copy import deep copy, import numpy as np, import pandas as pd. From matplotlib import pyplot as plt. As always, we import the required libraries. Okay, so let me continue. plt.rcparams square brackets figure.figsize close square brackets equals brackets 16, 9 close brackets, plt.style.use brackets, ggplot, close brackets. And that's it for the first step. Now, let's get the annual income and spending score values using the following lines of code. Getting the values and plotting it. F1 equals data, square brackets, annual income, brackets, K dollar, close brackets, close square brackets, dot values. F2 equals data, square brackets, spending score, brackets, 1 to 100, close brackets, close square brackets, dot values. Then we check the names of the columns using the for loop. For key in data.keys brackets, print brackets key, x equals np.array brackets list brackets zip brackets f1 comma f2 close all brackets. Then I keep a note of what x looks like. X equals square brackets 1 comma 1 close square brackets comma square brackets 1 comma 2 close square brackets comma square brackets 3 comma 3 close square brackets comma square brackets 4 comma 4 close all square brackets. plt.scatter brackets f1 comma f2 comma c equals black comma s equals 20 close brackets. We run this cell and here you go. So what did I just do? I printed all the keys in our data, which are customer ID, gender, age, and so on. Following that, I defined a NumPy array and zipped the values of the lists F1 and F2. I also left a comment of how X looks like. We then plotted a scatter graph to see how much our data is scattered. You can see it in the output graph. Now, in the next lecture, we will be training our models and we'll visualize the clusterings. Now, in our fifth implementation step, we will define the classifier. First, we import it. From sklearn.cluster, import the k-means algorithm. Then we will create our classifier with a number of clusters equals 3. So I write numbers of clusters. K-means equals k-means brackets n underscore clusters equals 3 close brackets. Following that, we will be training our model using the fit brackets method and by providing our training data X. So I keep a note here, fitting the input data, k-means equals k-means dot fit brackets X. Next, we predict the performance of our model on X and store the labels. Getting the cluster labels equals k-means dot predict brackets X. Then we create the clusters using dot clusters underscore centers underscore and print the values. Centroid values, centroids equals k-means dot cluster underscore centers underscore. These are the coordinates of the clusters and they are consistent with our labels. In the next lectures, we will plot the clusters. Let's visualize the cluster values of the X data. So first, let me write the necessary code. Fig equals plt.figure brackets. AX equals axes 3D brackets fig. Ax dot scatter brackets X square brackets colon comma 0 close square brackets comma X square brackets colon comma 1 close square brackets comma X square brackets colon comma 2 close square brackets close all brackets. Here we first define a figure using plt.figure brackets. Then we defined a 2D axis inside the figure. After which we created the scatter plot for our x values for 3 attributes. The code x square brackets colon comma 0 close square brackets is the first category. X square brackets colon comma 1 close square brackets the second, and so on. We reach our last implementation step in plotting our clusters. Our k-mean is predicted on the data set X. We use the same code as previously. We first define a figure using fig equals plt.figure brackets. Then ax equals axes 3D brackets fig. Here we define a 3D plot inside the figure. After which ax.scatter brackets x square brackets colon comma 0 close square brackets comma x square brackets colon comma 1 close square brackets comma x square brackets colon comma 2 close square brackets comma c equals y close all brackets. Here, we created the scatter plot for our x values for 3 attributes. The code x square brackets colon comma 0 close square brackets is the first category of our data. X square brackets colon comma 1 close square brackets the second, and so on. Ax.scatter brackets c square brackets colon 0 close square brackets comma c square brackets colon comma 1 close square brackets comma c square brackets colon 2 close square brackets comma marker equals star comma c equals number sign 050505 comma s equals 100 close brackets. C square brackets colon comma 0 close square brackets is the first category of our predicted data. C square brackets colon comma 1 close square brackets the second, and so on. Marker equals star. The stars show the center of our clusters. C equals number sign 050505 is the color, and S equals 1000 is taking 1000 samples from the predicted values. In this slide first, we initialized our k-means algorithm. K-means equals k-means brackets n underscore cluster equals 4 close brackets. We set our number of clusters to 4, which means the k-means algorithm will categorize our values into 4 clusters. Then we write k-means equals k-means dot fit brackets x. Train our k-means algorithm on the x data. After training, we will predict the cluster for other data points. So now, to predict the clusters, I'm going to write labels equals k-means dot predict brackets x. Here we are sorting the clusters of each data point into a variable called labels. Then we print labels. Print brackets labels. This line of code prints all the clusters numbers into which our trained model categorizes the data points. As we can see, we have cluster values from 0 to 4. This is because we define numbers of clusters equal to 4. Let's see if you can answer this question. Which of the following is required by k-means clustering? A. Defined distance metric. B. Number of clusters. C. Initial guess as to cluster centroids. D. All of the above. All of the above, because k-means clustering follows the partitioning approach. By partitioning approach, it is meant that k-means use all the steps to categorize related data points to a cluster. To do this, it uses option A, B, and C. Our last section is the recommender system. So what is the recommender system? Recommender system are algorithms aimed at suggesting relevant items to users. For example, items can be movies to watch, text to read, products to buy, or anything else depending on the industry. So what are the applications for this system? The applications of recommender system include movies, music, books, website, and television programs. Netflix, Amazon, LinkedIn, Twitter, and Facebook are using recommender systems in their software for different purposes. Now, what are the benefits of recommender systems? Recommender systems increase customer engagement. They increase the customer satisfaction by delivering relevant content. For example, Amazon can show all the relevant products to their customers, and in a similar fashion, Netflix can recommend your movies depending on your interests. Recommender systems reduce the time of content searching. In fact, you'll just have to select your favorite movies from the recommended movies. So what are the collaborative filtering recommendation systems? The collaborative filtering method predicts the interests of a user on a product by collecting preferences information from many other users. We can see that user 1 liked movie 1, movie 2, and movie 3, and users 2 liked movie 1 and movie 2. Based on the collaborative filtering method, the system will recommend movie 3 to user 2. Now, what are content-based recommender systems? Content-based filtering method utilizes product features to recommend other products like what the user likes, based on other users' previous actions or explicit feedback such as rating on products. As we can see in this diagram, that U1, which is user 1, likes two movies M1 and M2. The genre for both movies is adventurous movies. In such scenario, content-based recommended systems will choose an adventurous movie for user 1 as a next suggestion. Let's discuss the implementation of the recommender systems in Python. So the first implementation step is to import the libraries and to import the datasets. As usual, I'll need to write the following. Import numpy as np. Import pandas as pd. Import seaborn as sns. After importing numpy, pandas, and seaborn, we will use the libraries to get the datasets. We will have two datasets in this example, u.data and movie underscore id underscore titles. So let me first get the data from u.data by writing the following. Column underscore names equals square brackets user underscore id, comma, item underscore id, comma, rating, comma, timestamp, close all brackets. df equals pd.read underscore csv brackets u.data, comma, sep equals // T, comma, names equals column underscore names, close brackets, df dot head brackets. And we run this cell. So here you can see the data from u.data. So we can see that for this dataset, the user data contains an item ID, a user ID, rating of the movie, and the timestamp of the rating. We use pandas to import our CSV file. So basically, it is just the .read underscore CSV function that helped us import the data. Also, we can specify the columns we want to import. In our case, it is user ID, item ID, rating, and timestamp. We then use the head method of the pandas library to see the first 5 rows of our data. Now, let's get the data from the data set that contains the movie's ID and titles. Movie underscore titles equals pd.read underscore CSV brackets movie underscore ID underscore titles close bracket movie underscore titles dot head brackets. We can see item number 1 is Tony Story. Then for item number 2, its title is GoldenEye, and so on. So after importing both datasets, we will merge them into one data frame using the common item ID. We will use the merge method from the pandas library. So I'll write the following. df equals pd.merge brackets df comma movie underscore titles comma on equals item underscore id close brackets df dot head brackets. Again, we can check our data by using the dot head brackets method for pandas. After merging our datasets into a single one, we'll sort the rows by group of title and rating. Then we'll find the count and mean of all the ratings on a given title. So let me write the needed lines of code. Let's create a rating data frame with the average rating and number of ratings. df.group by brackets title close brackets square brackets rating close square brackets dot mean brackets dot sort underscore values brackets ascending equals false close brackets dot head brackets. We run this cell. df.group by brackets title square brackets rating dot count brackets dot sort underscore values brackets ascending equals false dot head brackets. We run this cell. So basically, we use the group by method to group our data by title and rating. Then we counted all the ratings on the given titles. And then we sorted the values in descending order, as you can see. And finally, we printed our data using the dot head brackets function. So, as you can see, we got all accounts for the titles. 584 ratings for Star Wars, 1977. 509 ratings for Contract, 1997. 508 ratings for Fargo, 1996, and so on. Following that, we also found the mean of the rating using the dot mean brackets function, as you can see on screen. Alright, now on to the next step. We sort the rows by group of titles and rating. We put all the ratings as a data frame into our rating variable, and we got the mean of all the ratings. We can see that for each title we have a corresponding rating. For example, for the title Till, there was U 1997. The mean of the ratings is 2.333. Now, after getting all the mean ratings, we will add a new column to this data frame. And we will put the number of ratings available for each movie. So let me write the needed code. Ratings, square brackets, num of ratings equals pd.dataframe brackets df.group by brackets title square brackets rating dot count close all brackets rating dot head brackets, and we run this cell. As you can see, we added a new column and we called it number of ratings. We put all the counts of each ratings in this column. For example, for the movie Till, there was U 1997. You can see that only 9 users rated this movie. Similarly, the movie 12 Angry Men 1957 was rated by 125 users. This gives us a clear picture of how many users rated the movie and what is the significance of the rating. Now let's plot a histogram that will show us the number of ratings. So to do that, I'll write the following code. plt.figure brackets fig size equals brackets 10, 4 close brackets ratings square brackets num of ratings close square brackets dot hist brackets bins equals 70 close brackets. We run this cell, and here you go. We use the .hist brackets method to plot this histogram. And as you can see, we have a maximum rating of 500 users for a movie. Now, let me create a histogram for the ratings. This will allow us to see how many users choose a rating of 1, how many users choose a rating of 2, how many users choose a rating of 3, and so on. Alright, so to do this, I'll need to write the following piece of code. plt.figure brackets fig size equals brackets 10, 4 close brackets ratings square brackets rating dot hist brackets bins equals 70 close brackets. We run this cell. And here you go. We have our desired histogram. As you can see, we noticed that the maximum rating was 3 and that about 120 users rated the movies around 3 stars. So, to sum up, we simply took the ratings column from our data and plotted its histogram. Now we'll use the Seaborn library to plot a joint plot of the ratings and number of ratings. Alright, let me do this. sns.jointplot brackets x equals rating, y equals num of ratings, data equals ratings, alpha equals 0.5 close brackets. We run this cell, and here you go. We have the desired output. From this plot, we can clearly see that very few people rated a movie 5 stars. Now, when it comes to 4.5 stars, we see that around 600 ratings of 4.5 were given by the users. Also, we see that when it comes to 3 stars and 4 stars, we have higher amounts of ratings. Okay, now that we have a general idea of what the data looks like, let's move on and create a simple recommendation system. In this implementation step, we import the movie dataset and pre-process it. Alright, so let's create a matrix that has the user IDs on one axis and the movie title on another axis. Each cell will then consist of the rating the user gave to that movie. Note that there will be a lot of NaN values, because most people have not seen most of the movies. Okay, So to do this, we will use the .pivot underscore table and make a table with an index of user ID, titles as the columns, and the ratings as the values of our table. So I'll write movie mat equals df.pivot underscore table brackets index equals user underscore ID comma columns equals title comma values equals rating close brackets movie mat dot head brackets. We run this cell, and here you go. We have the desired output. Each cell will then consist of the rating the user gave to that movie, and we can see the data by using the dot head method. As said previously, there are some null values in our data, and these values are null because most people have not seen most of the movies and have not rated them. We have to pre-process this data and make it clean. But before that, let's sort the most rated movies. Let's sort the most rated movies using the dot sort underscore values on the number of ratings, and then let's print the first 10 values. Ratings dot sort underscore values brackets num of ratings comma ascending equals false close brackets dot head brackets 10 close brackets. We run this cell. We can see that the top rated movie was Star Wars 1977 with the number of ratings equal to 584 and an average rating of 4.359. The second is Contact 1977 with a rating of 3.80 and it's rated by 509 people. Let's grab the user ratings for these two movies. We will find the column of Star Wars 1977 in our data set, movie mat, and similarly for the Liar Liar 1997 movie. Alright, let me write Star Wars underscore user underscore ratings equals movie mat square brackets Star Wars brackets 1977 close square brackets Liar Liar underscore user underscore ratings equals movie mat square brackets Liar Liar brackets 1997 close square brackets Star Wars underscore user underscore ratings dot head brackets. We run this cell. We can see that for user ID 3 there is no rating, and this will create some errors that we will see later. Now we will use call with brackets method to get the correlation between our most rated movies. Similar underscore to underscore Star Wars equals movie mat dot call with brackets Star Wars underscore user underscore ratings close brackets. Similar underscore to underscore Liar Liar equals movie mat dot call with brackets Liar Liar underscore user underscore ratings close brackets. And we get an error. The error says runtime warning brackets 0 n counted. This was because of the null values in our table. So let's remove the errors. Now we will create another data frame with arguments that contain the similar _to _Star Wars variable, as well as the correlation column. core_Star Wars equals pd.dataframe brackets similar _to _Star Wars, comma, columns equals square brackets correlation close brackets core_Star Wars dot drop na brackets in place equals true close brackets core_Star Wars dot head brackets. We run this cell, and here you go. So we dropped all the null values using .dropner. The in place equals true will make the changes in the data frame itself. If it is equal to false, it will create a new data frame. So let's sort out our data on the basis of correlation. core_Star Wars dot sort underscore values brackets correlation comma ascending equals false close brackets dot head brackets 10. We run this cell. Now if we sort the data frame by correlation, we should get the more similar movies. However, note that we could get some results that don't really make sense. This is because there are a lot of movies only watched once by users who also watch Star Wars. It was the most popular movie. We can fix this by filtering the movies that have less than 100 reviews. Okay, so let's now fix this by filtering out the movies that have less than 100 reviews. This value was chosen based off the histogram plotted earlier. core_Star Wars equals core_Star Wars dot join brackets rating square brackets num of ratings close all brackets core_Star Wars dot head brackets, and we run this cell. Then we finally sort the values and notice how the titles make a lot more sense. core_Star Wars square brackets core_Star Wars square brackets num of ratings close square bracket greater than 100 close all square brackets dot sort underscore values brackets correlation comma ascending equals false close brackets head brackets, and we run this cell. Here we used a number of ratings greater than 100 and then we sorted the values based on correlation. When printing our data, we can see that the number of ratings for Star Wars is 584. And it has a correlation of 100%, and then after that we have another movies. Doing the same steps for the Liar Liar 1997 movie, we write core_Liar Liar equals pd.dataframe brackets similar _to _Liar Liar comma columns equals square brackets correlation close square brackets close all brackets core_Liar Liar dot drop na brackets in place equals true close brackets core_Liar Liar equals core_Liar Liar dot join brackets ratings square brackets num of ratings close all brackets core_Liar Liar square brackets core_Liar Liar square brackets num of ratings close square brackets greater than 100, close all square brackets, dot sort underscore values, brackets, correlation, comma, ascending, equals false, close brackets, dot head brackets. And we run this cell. We can see that it has a number of 485 ratings, with a correlation of 100%. And then, after that, we have other movies. Here is the last quiz for you. Why are recommendations engines becoming popular? A. Users have less time, more options, and face an information overload. B. It is mandatory to have a recommendation engine as per telecom rules. C. It is better to recommend than ask user to search on cell phones. D. Users don't know what they want. And the answer is recommendations engines are becoming popular because users have less time, more options, and face an information overload.